Okay, so in the second video here, I'm going to talk about what a corner point is. Some texts actually call them vertices, but but basically, corner points, you actually find the intersection of the lines, and that's what yields the corner point. So let's look at a region and identify the corner points. Let's take a look at this one. We have to find where 2x plus y is less than or equal to 22. And you already know how to do this, so let's not spend a lot of time on this. The intercept's the point 0, 22, which would be about right here, and then 11, 0 would be right here, and then if you test the point 0, 0, you'll see that you shade this side. The next inequality is x plus y is less than or equal to 13, which has boundary x plus y equal 13. So that goes through this point 0, 13, and this point 13, 0. You draw your line. And then if you test the origin 0, 0 here, you'll see that you have to shade everything below this line. Well, if you shade everything below that line plus everything below that line, the overlap is going to be in this dark purple region here. So that's the overlap so far. Well, then I have to bring in another inequality, 2x plus 5y is less than or equal to 50. And the intercepts for that are 0, 10, and 25, 0. Well, you can see 0, 10 is right here, and 25, 0 is actually way out here somewhere. So when I test the origin 0, 0 for that one, I got another true statement. So now not only am I shading everything, now I'm shading everything below the green line, everything below the purple line, and everything below the red line, and so that dark green region would be what I have now. Now normally that dark green region would go on infinitely across the origin, but remember, anytime that you have x and y also greater than or equal to 0, it restricts you to the first quadrant. So your solution region looks like this. So restricting it to the first quadrant, you're bounded here by the y-axis and down here by the x-axis. Then you have this piece, and then it turns here at this point, and then it turns here at this point. Now, in order to find the vertices or the corner points, 3 of them are kind of obvious because we used them in graphing. We know this point is 0, 10, so that's why it's important to label your graphs 0, 10. We know that this point here is the point 11, 0. And we know that this point here is just the origin 0, 0. Okay, but these 2 points require a little work. What you have to do is you have to figure out where these 2 points come from. So let's start with the point 9, 4 that I got. I got the point 9, 4 by looking at what lines made up that point. So notice that the line, this red line is the line 2x plus y equal 22. And then the other line, the purple line, or the blue line, whatever color it is, was the point x plus y equal 13. And the intersection of those points make up the line 9, 4. Now, if you do a good graph, you can probably just eyeball it to determine that they intersect at 9, 4. But there's no guarantee that the intersection will always be at nice round numbers. So what you need to do is reach back into your bag of tricks from an earlier chapter and remember how to solve a system of equations. Now I tell my students, once we get to this type of stuff, they can use the cheat keys on the calculator where you type in the augmented matrix and then just do RREF. So I've already tested them on how to solve systems of equations. So I don't really care how they get these answers as long as they figure out that these 2 equations, where these 2 equations have a simultaneous solution, is the answer. And so that's 9, 4. And by the way, you should really check it. 2 times 9 plus 4 is 22, and 9 plus 4 is 13. So that is the solution. So that's the intersection of those 2 lines, which gives me that corner point. Now this corner point is the green line and the blue line or purple line. Well, we know the purple line is x plus y equal 13, and the green line is 2x plus y equal 50. So now I have to solve that system. And again, you can solve that system using matrices, or you can use the elimination or addition, what's called the elimination or addition method. Or maybe you could solve for y here and then plug it back in here and use substitution. Again, I don't care, but you have to find out where these two lines intersect in order to get the solution. And so they intersect at the point 5, 8. And you can check it. 5 plus 8 is 13. And then 2 times 5 plus 5 times 8 is 50. So those are 1, 2, 3, 4, 5 corner points of this region. Now I do want to mention that not every point of intersection is a corner point. Notice that the red line and the green line intersection is not part of the region. So that's not a corner point. And notice that these points that cross the axes way out here, like here and up here, there's a couple points up here, those aren't part of the region, so those aren't corner points. So what I'm trying to say is not every intersection is a corner point, but corner points can only occur at the intersections of the lines or the axes. We did this one before on the first video, but what we had done is we didn't have these last two where I have x and y is greater than or equal to 0. I guess to be consistent, that should have said x1 and x2 should have been greater than or equal to 0. But basically, I think you get my point. So that means we're restricted to the first quadrant. Let's jump back up here where that problem was. You might remember that we had determined that without the x and y or x1, x2 constraints, we had this purple region that went out forever. Well, now if you only restrict it to the first quadrant, then what you're going to get is you're going to get a region whose boundary looks like this. Okay, so that's kind of a rough picture there, but you see those three lines that make a triangle? So that's the boundary region. Now we can see two corner points real easy, 5, 0 and 7, 0. But we need to figure out which two lines make up this corner point. Well, it's got to be the line that went through 5, 0 and the line that went through 7, 0. So that would have been the line that went through 7, 0 was 3x1 plus 3x2 equal 21. And the one that went through 5, 0 was 4x1 plus 2x2 equal 20. So those two lines give us the intersection. So basically what I had to do was I had to solve the equation. I had to, take this, let's make that an equation, let's make this an equation. So basically I had to find where these two equations or two lines cross, and it turns out they cross at the point 3, 4. And you can check that. 3 times 3 plus 3 times 4 is 21. And then 4 times 3 is 12. And 2 times 4 is 8. And 12 plus 8 is 20. So basically I get 3 points of intersection that are actually called corner points. Okay. Now, one thing I want to say about this region, actually both of the regions that I did, this region right here is actually called a bounded region because I can draw a circle around it. Same thing here. This is a bounded region because I can enclose it in a circle. Now up here, if we go back to this guy, if you remember the original graph without the x and y being greater than or equal to 0, let's see if I can. Okay, well, before I had that constraint, this was an unbounded region, because if you say I can draw a circle around it, well, that wasn't true, because remember, this region went on forever and ever and ever. Okay, so it didn't become a bounded region until I threw in those constraints about x1 and x2 being greater than or equal to 0. Okay, so let me end this video with a note about linear programming. Linear programming is a process where a function is optimized based on the points restricted to a specific region. For example, suppose we needed to maximize a revenue function like this, where we have revenue is 150x1 plus 200x2, and maybe x1 represents 3 speed bikes and x2 represents 5 speed bikes, and we could only use values above in this triangular region up here. Okay, well, the region itself contains a lot of points. I mean, if you think about it, if I can find my mouse, there we go. Alright, so there's lots of points in this region. And there's actually points on the boundary of the region as well. So there's lots of points on the boundary as well. Okay, so, missed there. Alright, but anyway, all the points on the boundary or in the region are the possible solutions. Well, that's infinitely many points. So obviously we haven't got time to plug in infinitely many points. But luckily, it turns out that someone was able to prove that if this function does have an optimal solution, if it does have a maximum, then it must occur at one of these 3 corner points. So basically, all we have to do is plug in the 3 corner points. So if I plug in the point 50, I get 750. If I plug in the point 70, I get 1050. And if I plug in the point 34, I get 1250. And now all I have to do is look for the maximum of those 3 numbers, which is 1250. So that would mean that I would need 3 3-speed bicycles and 4 5-speed bicycles to get a maximum revenue of $1,250. Now, we could also minimize a function using this method. The minimum would be 750, but in this particular example, you probably wouldn't want to minimize revenue. So we'll discuss this more in the next video.